Okay, we are looking at FRQ5, and this one is involving two different particles. We have the position function for particle P, which is given by this, and then you're given your velocity of particle Q by this function. Okay, so it's definitely, you want to make sure you know what you have. So for particle P, we have our position function. To get our velocity, we take the first derivative. To get the acceleration, we take our second derivative of that. For particle Q, you are given the velocity. So to find position, that's why you have to know something about it so we can work backwards and do the integral of our velocity. And then to find acceleration, we will take the derivative of that. So definitely make sure you're aware of what you have and keep straight what goes with what, okay? So for part A, it's just asking us for time equal or time greater than or equal to 0 and less than or equal to 8. When is the particle P moving to the left? Okay, what tells us when where a particle is moving, whether it's left or right? That's your velocity function, okay? So what we're looking for here in part A is when is the velocity, or when is our first derivative of our function x negative? Okay, so what we have to do is we need to find our first derivative here, okay? So x prime is going to equal 1 over the argument times the derivative of the inside, so there you're using chain rule. And if you want to factor that when you write it, just so it helps you find your critical values, go for it. Okay? So our first derivative is there. And our only critical value from that is t equal to 1. So x prime of p of t equals 0 when t equals 1, and it is never undefined. You can see your denominator doesn't factor. So when we set up our number line, we have x prime. Make sure you label it, and you're going to test values between 0 and 1, because notice it is for values including 0, including 8, okay? Over here, so if you test 0.5 and you plug it in there, you get a negative value. And if you plug in, like, let's say 2, you're going to get a positive value. So it will be moving to the left for times greater than or equal to 0, less than 1. So since this is true, the particle P is moving left. Okay, so that's part A. Part B says for values between 0 and 8, including it, find all times during which the two particles travel the same direction, okay? So right now, we know that from 0 to 1, particle P is moving left, and from 1 to 8, particle P is moving to the right, okay? So we just have to figure out when particle Q is moving left and right. So now what we're going to do is you're actually already given your velocity function for Q. And I am going to go ahead and factor that so I can find the critical values for the position function of particle Q. So we get t minus 5, t minus 3. So your critical values there are 3 and 5. So you want to test your values by plugging in, let's say if you plug in 1, you'll get a negative times a negative, which is a positive. If you plug in 4, you'll get a negative times a positive, so it's negative. And then when you plug in, let's say 6, you'll get a positive times a positive. Okay, so comparing that with the one in red over here, you want to look for at what point do you have the same signs. Okay, so we're at 1, and that's it. So when looking here, when do they have the same signs? Let's see here. They're both positive in this little portion here from 1 to 3, and then they're both positive from 5 to 8. So we'll include both of those intervals. So both particles move in the same direction for time between 1 and 3 and between 5 and 8. And we are going to include 8 because that's where this is cut off, and this is where these functions are defined for time equals 0 to 8 inclusive. So, and then we need to say both particles move in the same direction for those times because x prime and have the same signs. Okay, next up for part C, we're just using particle Q. It says find the acceleration of particle Q at time 2. Is the speed of particle Q increasing, decreasing, or neither? Explain your reasoning, okay? So, to find the acceleration, that's our second derivative. That is the rate of change of our velocity. So for Q, you were given velocity. So what we need to do is find our rate of change of our velocity function for Q. So you started with the velocity of position Q was t squared minus 8t plus 15. So to find our acceleration of Q, we're going to let that equal v prime, which equals 2t minus 8. So to find the acceleration at time equals 2, we just go ahead and plug it in. Oops. Which gives us a negative 4. So at time equals 2, our acceleration is negative. So find the acceleration. So that's the first part. And then we have to decide whether it's increasing, decreasing, or neither. So what we know is that the acceleration at time equals 2 is negative. And the velocity at time equals 2, so you can even go back up and look at your number line, at 2 is positive. So since they are opposite signs, the particle is slowing down. And I need to get rid of this little equal sign here. Won't let me? Oh, won't let me. Okay, let's get rid of that. Okay, so think about that. Your rate of change is positive. Your rate of change is negative, meaning it's concave down. So at time equals 2, it is increasing, but concave down. And so you can see how the particle at that time is going to be slowing down. Okay? Okay, and in part D, we're still working with particle Q only. So it says find the position of particle Q the first time it changes direction. So we know if we're looking at our velocity of Q, it starts off traveling right until 3 seconds, and then it travels left, and then when it hits 5 seconds, it travels right. So we want to know the position at the first time it changes direction. So what does that mean? We want to find the position of Q at time equals 3. So we need to find our position function, okay? Your position function of Q is the antiderivative of your velocity function. And how do we find our antiderivative of our velocity function? We take the integral of it, okay? So that's going to give us t cubed over 3 minus 8t squared over 2 plus 15t plus c. And we want our particular solution here. We do have a given from the beginning. Particle Q is at position x equals 5 when time equals 0. So when we plug in 0 for t, the position of particle Q is 5. And that's how we get c equals 5. So our position function is t cubed over 3 minus 4t squared plus 15t plus 5. And we want to evaluate the position of particle Q at 3 seconds, or it doesn't even tell us if it's seconds or minutes, but at time equals 3, because that's when it first changes sign. And we know that again based on our velocity function and our critical values that came from our velocity function. So when we plug in 3, we get 9 minus 36 plus 45 plus 5, and the position is at 23.